For my final project, I developed a methodology of optimizing hybrid trajectories for an underactuated skateboarding system to perform simple tricks. The most simple and ubiquitous skateboarding trick is an ollie. Riders manipulate the board using the contact forces on their feet, essentially shifting their weight backwards to kick off the ground and into the air. This system can be abstracted to 2D and simplified by controlling the position of a point mass relative to the board with a motor. This motor can then be used to directly impose torque upon the board, without requiring two foot reaction forces. In effect, the angle of the point mass can be controlled to change the position and orientation of the board. The dynamics of the system were determined by hand using the free body diagrams shown below. Wheels were assumed massless relative to the board and rider, allowing friction to be ignored. Contact modes over the course of the jump were used to constrain optimization. The board starts out flat, shifting all its weight backwards until it begins to tilt. The back kicks off the ground after this and into the air, landing front first. Nonlinear constraints are used to ensure that the wheels remain on the ground when they should, such that when the board tilts up, it rotates about the axle of its back wheel. The board's kickoff is modeled as an inelastic collision. The tail end of the board smacks off the ground, reversing its angular velocity. Kinetic losses are accounted for using a coefficient of restitution. This guard function is used to reset state between ground and flight phases. After contact constraints and input limits were imposed, the optimization problem was solved using iPopt and PyDrake. This determined board state, control angle, reaction forces, and length of time step h between t discrete points. Ollie results were generated for a half-meter jump height over standard board dimensions and weight. Height is measured from the ground to the center of mass of the board, and jumps are constrained such that their max height must be equivalent to the height provided. Trajectories were generated over a number of jump heights. We see that takeoff is relatively consistent, but higher jumps require higher angular speeds on kickoff. When landing, higher jumps require larger oscillation amplitudes of control angle to balance the board. Different jump heights can be supplied to the optimization problem, but nothing can be solved over a half a meter due to acceleration constraints on the control angle. A manual is another simple skateboarding trick where a rider balances their weight backwards to tilt the board up while moving forward, basically identical to an ollie before kickoff. As one can see, contact constraints are quite similar between the two tricks. To impose a constant angle, the orientation of the board's velocity, phi dot, is restricted to 0 over the middle of the trick. Results were generated and a simulation can be shown below. Here you can see that the board continues to move forward while its angle remains relatively consistent. The resulting trajectory confirms this. The control angle holds the rider's center of mass at a nearly stable angle, holding the board tilted up at a constant angle during the middle of the trick. Future work could be done to improve this system. The acceleration of the control input was limited underneath a constant value. This could be improved to model a real motor's torque speed curve instead of taking on a simple value. Furthermore, the system is in 2 dimensions. Moving to 3D would expand the number of possible tricks to include things like a pop shove, which is shown below. Friction could also be included. If the wheels weren't considered massless, this would be a more realistic modeling of the system. If all this went well, a real system could be developed and tested.